would like you to do as part of the do now. I'll give you about 10 minutes to get through this. But it's the question that he is asked is, what would happen if you tried to hit a baseball pitched at 90% the speed of light? And so he doesn't talk so much about what hitting the baseball is like, more what's going to happen when this baseball tries to travel that fast through the air in our atmosphere. And so I'd like you to read this and then answer the questions that are on a little Canvas quiz that is the next link down. So the first link is to the article. The bullet point right here, it says, based on the reading, answer U4 light do now questions. I think it gives points, but this isn't going to be graded. This is just a practice quiz. So read the article, answer the questions. I'll give you about 10 minutes to work on that first task, and then we'll reconvene to review it. I'll be listening if you have any questions. So 10 minutes, go for it. Kiddos, 10 minutes has elapsed, so let's all come back together. Looks like 11 of you have submitted answers, so should be 2 more people still working on it, but if you're wrapping up, just finish up. All right, what'd you think of the article? Anyone read What If, the book that he wrote? It's a fun one to check out if you're into science stuff. It's a lot more physics. He's one of these kind of funny stories of Randall Munroe, the guy who wrote this, is a physicist who then started drawing these little stick figure comics, and he ended up making more money doing that than doing physics research. And so he's kind of dedicated himself to doing that now, but he's a pretty smart guy. You should check out the XKCD site. So, all right, so let's see if you figured it out. Anyone catch on? What's 0.9 C? What did he mean when the ball?
90% of light speed.
Yeah, there you go. So the 0.9 is the 90%, and the little letter C actually represents the speed of light. The next question then was, what speed is that? So 90% the speed of light, in something we could understand, miles per hour, what did it end up being?
604 million or something like that?
Yep, 604 million, which is a hard speed to try to wrap your mind around. That is unimaginably fast. That's pretty much faster than any form of matter could ever go. Does anyone know the actual value of C in meters per second? It was one of the options there. Does anyone know the speed of light in meters per second? It's about 300 million meters per second, which is insane. And again, not anything that I think any form of matter will be able to accelerate to that point, but 90%, who knows? So let's assume the pitcher could actually do that. If the ball, once it was released from the pitcher's hand, literally started to go at 604 million miles per hour, what would happen? So what would catch on? Anyone get that? Good, that's all my other students do this. What does this mean?
What? Would it blow up? Like,
it would blow up, but why? What's happening?
The air particles aren't fast enough to move away, so the ball smacks into them, and then they fuse with their atoms, and then it causes.
Yeah, it's a fusion reaction, which is actually a type of nuclear reaction. Fusion is the same type of thing that's actually happening in our sun. The sun is fusing hydrogen atoms to form helium atoms. This isn't exactly what the baseball would be doing, but it would basically be creating a very small star. You would be creating a massive explosion, blinding light. You would basically have this like X-rays and gamma rays in a shockwave basically traveling off the ball almost immediately. I like his little comic book animation of the disintegrating pitcher behind the pitch, which is crazy. But so, all right, if that's all happening, then give me some of the reasons. What are some of the reasons why the batter would never be able to hit the ball? There were a few.
When light comes, he wouldn't react because light wouldn't.
Yeah, so literally as he saw the ball leave the pitcher's hand, the ball would arrive, which I think that part's funny. Molly, what'd you catch on to?
Once the ball hits the bat, it pushes like the batter, the catcher, and the plate, and like everything. They
literally would have all been blown away by the shockwave, probably even before the ball arrived. Also, I keep saying the ball arrived, but that's not actually what's going to arrive to the batter. What's going to be, anyone see what's going to be left of the ball?
It's like a bullet shape.
Yeah, little piece of plasma that's basically rapidly expanding too. So yeah, so not a good situation. And then the last part he ends with is basically, well, according to the rule book, if you were hit by the pitcher in this situation, you could advance to first base. Why is that not going to be possible?
Stadium wouldn't be there.
Yes, the stadium would now be a crater, first base, and everyone else would be gone. So, yeah, so hopefully that won't happen. However, just a new question to pitch at you. What if we had this exact same scenario, but in the vacuum of space? Would it be a different situation if it was in space, which is a vacuum where there's no gas? What do you think? Think you get the same explosion?
There's no air particles, then gamma
Yeah.
wouldn't get sent off. So no.
Yeah, again, that's something that I was wondering if he would take it on that tangent. But I guess if there's no air particles, then theoretically the ball could launch off. It would probably eventually hit something or get picked up by something gravity-wise. I don't know. It's kind of an interesting thing to think about. But all right. So we're going to be talking today about some stuff that's relevant to that. That was kind of an extreme example. But before I get into new content, I want to take some time to look over the quiz that you all took right before we left on break. In fact, what I encourage you now, if you haven't done so already, on your Canvas, you should go to the science page, and you can either look for the quiz again under assignments or under quizzes. If you click on it, it should now be graded. And in fact, I typed some feedback to some of you on some of the questions. So if you want, you should go look at the quiz and see how you did and see the feedback that I typed. You can also click on grades. I spent most of the long weekend making sure catching up on grading stuff. And so you can check on missing assignments and just where you're standing right now. Things should be pretty much up to date now. I graded the presentations, I graded all that stuff. So it's good to take some time to do that right now. I want to look over the quiz. Everyone did really well on it. The first few questions were related to the Ocean Issues project. Did anyone recognize, had you seen these questions before?
Oh yeah, they were like the different quizzes for the separate.
Yep. Yeah, I tried to pull it from that. There might have been one or two new answers or new spins I put on it, but yes, birds die from oil exposure because their feathers are totally ruined, and so they can't insulate, they can't fly, they can't float. All of those were good answers. Food chains, biomagnification, organisms at the top are most threatened. And so I know this mentions things like eagles and killer whales, but does anyone know what other organism is affected and why you should be nervous? What else is at the top of the food chain?
Us.
Yes, so we are definitely also heavily exposed to biomagnification. The eutrophication question, everyone did great on. I saw sometimes some people, you put the last step as the first step, that the fertilizer shows up at the end, not the beginning, but that was worth 2 points, and I never took off the -2. You should only have -1 on that question if you messed up any of the order. No one got it completely wrong. Crabs are the ones that don't belong to the mollusk subphylum. Does anyone know where crabs belong? What grouping do we put them in? The hint is that they're a type of crustacean, but one level up from that starts with an A. It's because they have an exoskeleton. Yeah, arthropods. Yeah, so arthropoda I think is a subphylum, and then crustacea I think is after, it's the order or something like that. So, but yes, that's all relevant. But yeah, but the crabs do not fit in with that group. You all had to choose a different ocean issue. It was kind of funny to see that almost everybody went with either plastic pollution or what was the other one that was common? It was plastic pollution and the overfishing. Those were the two that were like almost always chosen. But as long as you had a good detailed explanation, gave you full points on that. If you had something missing, I might have taken off 1 point. The next question about the space station and the apple, again, you had to mention tangential velocity and define it, right, to get the full points there, that they're moving sideways. And this is something we're going to be exploring in more detail today about exactly what's going on with satellites in orbit. For the two friends, Kelly is more correct, and I'm hoping, just by even studying the equation, which some people mentioned, gravity only depends on mass and distance. It has nothing to do with atmosphere. There's as much gravity out in space, when you're 150 kilometers off of Earth's surface, you've got as much gravity affecting you there as you do on the surface of the planet. I think that was kind of a common misunderstanding from this unit and on this quiz. That's something I'm going to kind of try to keep reinforcing. And the reason astronauts are weightless is because they are in free fall. This, I think, a lot of you were able to define weight and define mass, which is great. But then explaining that, if you're massless, you're not there. Most of you got that. But to be weightless, again, a lot of you were still saying, oh, there's just less gravity or there's no gravity in space, and that's not the case. An astronaut in space is experiencing as much gravity as you do on the ground. It's just that they're in free fall. It's just like that OK Go video, but in that music video, the band, they only experienced weightlessness for about 27 seconds as the plane was in free dive. Astronauts are experiencing that permanently because they're falling around the planet in orbit inside of the shuttle or space station or whatever they're in. And again, this is something we're going to continue to explore today and with the rest of this chapter 5 unit. Everyone did great on this, understanding that mass is directly proportional, heavier, bigger mass, and distance is inversely proportional. The OK Go video, all of you got that it wasn't filmed in zero gravity, they're just in free fall. As long as you had some reference to that, that was good. The ear gives us our sense of balance. Again, some of you were still talking about hearing, which yes, the ear does, but the reason we were talking about it was for your sense of direction and acceleration. And then the flip grid activity, again, almost everybody did either the bending over to touch your toes with the center of gravity thing and your base, or the little hole in the bottom of the cup. Those were the videos I was watching. But again, if you go to Flipgrid and look at your video, I left you a little comment, told you your score out of 5 points. Typically only took off 1 or 2 points if your explanation seemed to be lacking some detail. And the extra credit, if you tried it, I gave you 1 point, even if it was incorrect. If you did get it correct, I gave you the full 3 points. Common mistake on that was that a lot of people forgot to convert kilometers into meters, which you have to do to use that the same value for the gravitational constant G. That was it. Out of 35 points, your scores should be available to you on Canvas. Any questions on that? Or anything else you'd like to look over? All right. How'd you feel about a Canvas quiz? Have you guys done Canvas quizzes in other classes that all seem to work well? All right. I think this is the way we'll do assessments for the rest of the year. I don't think I'll give you like a final exam in this exact format. I think that's too long, but we'll figure something out when we come to that. So, all right. So the next thing I want to do is a little activity relating again to the last few parts of chapter 5. So back on the tasks list on Canvas, just to show you here. We're now on step 3. What I'd like you to do is use the same projectile motion FET that we've been using before, the one that looks like this. The link for it is right there, and you're going to be using the intro for this first activity. But the link for it's right there under task 3. And then I'd like you to complete, again, just a short little quiz. It's literally just 3 questions on Canvas that relate to that. So it'll kind of give you instructions on what to do with the FET simulation and how to adjust the cannon. And you're just going to be making some observations in answering the questions. I'm going to give us about 8 minutes to do this, but I'll keep an eye on.
We're going the drag or intro one?
Sorry, actually, yeah, it might be the drag. I would just do whatever the instructions say. Yeah, sorry. It's probably the drag then, if that's the question. Yes. So yeah, you'll be going to that option, the third one on the bottom there for observing drag. So yeah, this is just meant to see what you know already. All right, again, I'm here listening if something doesn't work or if you've got a question. Otherwise, 8 minutes to go for it, and we'll reconvene to review. All right, about 8 minutes has passed. Looks like at least most of you, about 10 of you have responded. So those of you who are still working, just try to wrap it up. Let's come back on in. And what I'm going to do is actually dive right into just a couple of review slides that I want to go through to cover the content from these next few chapter 5 sections. And we'll touch on the activity and the questions that you just did as part of that. So feel free to take some notes on what I'm covering if you want, either in your digital notebook or in paper. I have made a video recording of myself going through these same slides that you can also watch later if you want to. And there's also always the class recording that you can watch. So this is content from chapter 5.9 all the way to 5.11. I'll present here. And what it's going to talk about is the idea of altitude and range with projectile motion, the effect of drag, which is what you're exploring using the activity, and also then looking at fast-moving projectiles, specifically what we call satellites. And that's going to lead us into the last part of the chapter and what we're going to be doing on Friday. And a lot of you are probably experienced with this just through video games on your cell phone. Anyone know what's the popular game that's pictured here? Angry Birds is literally just projectile motion. That's all it is. I don't know exactly how they simulate the physics in that game, but you're just firing projectiles and trying to knock things over and strategize. And a lot of sports like baseball and golf, projectile motion is really important. And so being able to understand these sorts of things is applicable in sports. So the first part of the activity, you were firing a cannon at sets of angles that I assigned to you. And so what did you notice about the landing site from these projectiles when you fired at these two angles? What was true about where the projectile landed when you fired at 25 and at 65?
At the
They
same
land at the
spot.
same spot.
Landed
Yep.
in the spot.
Yeah, same place where they landed. So kind of cool, something that I didn't realize. Did anyone catch on to the trend? What is true about 25 and 65, 40 and 50, 60 and 30? Anyone catch it?
They all add up to 90 degrees.
They all add up to 90 degrees. And again, this is something that was new to me. So any two angles that you're firing at, if they add up to 90 degrees, then that projectile will land in the exact same place, which is kind of interesting. A couple things that this is assuming. What was the position of the cannon? What had to be true about that?
0.
Yeah, it had to be level with the ground. So that's one important thing to observe, right? And the other thing is that they're completely ignoring something. What was not taken into account in the simulation? What are we ignoring that you then played with later?
Drag.
Yes. Yeah, there's no air resistance or drag. So this is sort of an ideal situation. But this does bring kind of two important things in mind. So when we're looking at projectile motion, these parabola shapes, there's two things you can consider. The altitude, what's that? What is the altitude of the projectile?
The height an object reaches
It is-
above the ground.
Yes, maximum height from relative to where it was fired from, right? That's the altitude it reaches. And that's again because it has force going upward, but it's slowed down by gravity vertically, and then it falls back down. Then there's the range. What's the range?
The distance it will go.
Yep, that's the horizontal, right? And so you're sort of making a big upside down capital T, right? We can always think about both altitude and range of any projectile. Why would it be important to be able to study the altitude and range of a projectile and then possibly even predict the altitude and range of a projectile? How's that relevant to, for example, think about what you're doing in this simulation. In history, why was that relevant? Why was it good to know about altitude and range of projectiles?
I know where to aim the cannon.
Yeah,
Like-
so cannons were used in warfare, right? And yeah, so being able to aim it correctly and hit a target from a distance, they had to take those things into account. And even in modern war, when they're using things like mortars, which are basically grenades that are fired into the air with a certain angle, there's a lot of coordination that goes into that. You usually have people out scouting a certain location, then giving the coordinates, and they have to get the altitude range just right, taking drag into account as well, and fire from there. So, but sports, it's also very relevant, right? Golf in particular is one that's all about altitude and range, trying to get the ball towards the hole. And baseball is more about throwing stuff, which we'll explore in a little bit too, because drag is more relevant to that. So, but yes, very good. You got at the idea that we are ignoring drag, and that's not something that should be ignored. So again, this is just summarizing what we just talked about, that it always adds up to 90. One other thing that I think is interesting to notice is that the speed is also consistent. Again, this is ignoring air drag. But if a projectile is fired at 40 meters per second from a level ground, it will be traveling 40 meters per second when it returns to that exact same height. You can kind of see how the speeds match. The only difference is that when it's fired, it's going upwards, and when it's returning to the ground, it's traveling downwards. But the speed is consistent. But again, I think when you bring drag into the picture, it's not that consistent. I would imagine that air drag kind of alters these numbers a little bit. Okay, so the last part then was you had to sort of just under the drag feature, fire one projectile and then make some adjustments and fire two more. And so the first shot was sort of your comparison. That was your baseline. That's this one right here. So what did you notice when you increased the drag coefficient to 0.80? What happened to the altitude and the range?
Lost both altitude and range.
Yep, so both are shortened. So that's kind of a simple way to think about drag, right? Drag is just shortening those two things, both altitude and range. So don't think of it as only affecting the range or only affecting the altitude. Both are impacted because the ball is constantly, or the projectile is constantly experiencing that. So what about then when you decreased the drag coefficient? What happened to the,
increased.
yeah, we increased drastically the altitude and the range. And that I think is kind of cool that they show you this sort of more aerodynamic projectile that can actually go a lot farther. And this is why you see certain designs in projectiles, right? You want them to be aerodynamic to reduce drag. In fact, again, going back to athletics, a golf ball, does anyone know what the surface of a golf ball is like? What does it look like?
It has a bunch of like little pits or
Yeah, those like little pits, little craters, right? Is that just for decoration?
no.
Yeah, no, it's all about aerodynamics. In fact, a golf ball is probably one of the most aerodynamic athletic, balls that are out there. Like if they were able to use golf balls in baseball, like if a pitcher was able to pitch a golf ball rather than the baseball, they would get much higher pitching speeds, like far past the world record. I mean, most really fast pitches in baseball are at about like 90 miles per hour or so, which is pretty insane to think about even that. But if they were throwing something like a golf ball, it would be even higher because it's much more aerodynamic than a baseball is. So kind of interesting to think about how that can, by changing the amount of drag, reducing the drag, you can get a lot more altitude and range from a projectile. So you can think of it as sort of, you have this ideal path, which is ignoring the effective drag, and then the actual path. And this is, again, the bane of, golfers are constantly battling with this, and baseball as well, trying to deliver the ball. If we were able to play sports where there was no air in a vacuum, like playing baseball on the moon, it would be a much crazier game because suddenly you'd be able to throw the ball much more efficiently. I think the book says like 6 times as far as you normally would when there's air drag affecting it. This also explains how different pitches work. And this is something that, again, was new to me. I'd always wondered, what's different about a fastball versus a curveball in baseball. And it is all about drag and how the ball is released from the hand. If a ball was just thrown, baseball, just thrown straight, no spinning whatsoever, you can see in this diagram here, drag is going to act equally on the ball and just slow it down. But if you add a little spin to it, all kinds of interesting things happen. And so this is what pitchers are doing constantly, is trying to add a little spin to the ball in different ways. This is how you throw a fastball or a curveball. And what that does is the side that is spinning into the forward motion, that's going to be getting the most drag, right? Air is acting on that as it spins through it. And there's less drag on the bottom part. And so it's sort of like an airplane's wing. This is going to adjust the height of the ball. And so a fastball actually doesn't fall down as much as a normal throw would, right? It's sort of almost resisting the pull of gravity. They call this the Magnus force over here, which you don't need to worry too much about that. It's just basically that there's a little bit of lift on the baseball. And you can see too by the wake here, this is kind of, I think of more almost like a curveball with this one. But the ball is going to follow a perfectly straight path. And again, think about it, if you're a pitcher, that's actually what you want to do, right? You want to try to trick the batter, make it really hard to hit the ball. And so if the batter's watching, if the ball's curving out and then back in again, it's much harder to swing at and hit. And so this is what pitchers are constantly doing, is trying to get their release just right, that the ball curves and moves strangely, but still ends up coming in right over home plate where it could be counted as a strike if the batter missed it. And again, it's all about drag. And so again, I wonder, then I guess that means you can't throw a fastball or throw a curveball in space, right, in a vacuum. That might be an interesting question to explore a little bit. I don't know if that's exactly possible. So, okay, the last part that I want to cover is now going to transition into what we call satellites and things that are orbiting our planet. And so there's a couple of things you kind of have to keep in mind about this. But before we dive into this, any questions on altitude, range, and drag? We feeling good there? Okay. So let me throw a situation at you. The book, again, sort of gives you this situation where you kind of have to take this as a given, that if we think about a projectile that's thrown and it has to fall 5 meters, so that's the set distance. Keep that in mind, that we have a vertical path from where it's thrown down to the ground of 5 meters. And the book says that on planet Earth, with our gravity, it takes exactly 1 second for that to happen. So it's always going to take 1 second to fall vertically 5 meters. However, the range that you're able to achieve in the throw can vary, right? It depends on how much power you put into that vertical throw, right? If we apply a lot of force to that horizontal velocity, then our projectile is going to travel a really big distance, versus if we didn't throw it with a lot of force, it wouldn't travel very far, even though, again, every single time it's still falling 5 meters and it's still always taking 1 second. So every single one of these throws that's pictured here took 1 second. It just traveled farther because it had a lot more horizontal velocity. So it went a lot farther in that 1 second of falling. So with that in mind, what do you notice about the ground in this picture? Is it perfectly flat?
It's more like a circle.
Everyone see how it's curving away? Now again, this is still debated amongst some people, but what would you say about the shape of Earth? Is it round or is it flat?
Round.
It's round. Okay, I just want to make sure. Do we have any flat earthers in this class? Because there are some people who still believe firmly that Earth is flat. But we're going to conclude that Earth is round. And in fact, the curvature of the Earth is, if we keep the same 5 meter scenario in mind, then it's going to curve away 5 meters for every 8,000 meters of horizontal distance. That's going to be a 5 meter curve from the horizontal. So can anyone give me 8,000 meters in kilometers? What would that be? Everyone with me that 8 kilometers is 8,000 meters. So this will be a much easier number to work with. What this means is that, just to use my excellent drawing skills here, if you were in a boat on the ocean, sailboat, over here, and you were looking out at the horizon, if there was another boat that was exactly 8 kilometers away, and it only had a mast that was 5 meters tall, which is pretty short for a sailboat, but let's just say that that boat has a mast that's only 5 meters tall. If you were over here looking out, would you be able to see that boat that was 8 kilometers away?
Probably not directly at it.
You just see the mast, right?
Yeah, you might be able to see the very top of the mast, but you would not see the boat. And that's because most of the boat is hidden below the curvature of the Earth, which I know is kind of a weird thing to think, but that's sort of what this means, right? Is that it's curving 5 meters down for every 8 kilometers of distance. That means that you wouldn't be able to see something that was 5 meters tall 8 kilometers away. It would be below the curvature of the Earth. So the new situation that I want to give to you now is, what would happen if you were, let's say now we're not in the ocean anymore, we're on solid ground, but if you were to stand here and if you were able to throw a baseball or some kind of projectile, right, with enough force that it would travel 8 kilometers or 8 meters for, again, what was the amount of time, remind me, that it takes for a projectile to fall 5 meters? What was the given time?
1 second.
1 second. So if you were able to throw a projectile over here that went approximately 8 kilometers, which is the same as 8,000 meters, if it went 8 kilometers per second, when would it touch the ground? When would that projectile fall to the ground? Sort of a trick question.
When would it touch the ground?
Mhm.
1 second.
That's 1,600 meters.
So if it was traveling
How
at,
long would it go before it touches the ground, or like how long it would take?
well, that's another good question, is how long would it take in order for it to touch the ground? So again, think about this. The ball that we just threw is traveling approximately 8 kilometers, and it's falling about 5 meters for every 8,000 kilometers. But remember, the Earth is also curving away at that exact same rate. The Earth is also curving 5 meters down for every 8,000 meters or 8 kilometers.
Is it about a mile?
So would it ever touch the ground?
No.
It would. That's sort of the trick question here. Granted, I think it's a better example for this. Our figure was a little bit higher up, but that's sort of the trick question that we're getting at here, is that if you were able to somehow achieve that, if you're able to throw a projectile at about 8 kilometers per second, it would never hit the ground because it would just be constantly falling around our planet, right? Because Earth is curving away at that exact same angle, basically. Again, kind of weird to think about, but you will have achieved what's called orbit, going around the planet. So here's kind of a silly drawing. Again, this is straight from the textbook. This wouldn't exactly be possible. I'll talk about why in a second, but you could theoretically hit yourself in the back of the head, or you could turn around and catch the exact same ball that you threw after it had traveled all the way around the planet that you were on. If anyone's a Rick and Morty fan, I think at the end of the second or third season, the whole family escapes to a planet. Does anyone know what was weird about that planet?
It was very small.
It's a super small planet, and there's a scene where Morty's playing frisbee with himself, where he chucks a frisbee and he turns around and catches it again. And it's the same idea that he has thrown that with enough force that it doesn't ever touch the ground. It circles around the planet and he catches it again. So that's essentially what's going on with orbit. So couple things then to consider. This invites this new vocab word, which I think is worth noting down, is a satellite. So that's what we call a satellite. Any projectile that is moving fast enough to fall continuously around Earth. So in other words, it might be something that was thrown or something that was launched, but it's never going to hit the ground. And that's what we call the satellite. It's orbiting the planet. So the minimum necessary speed to orbit Earth is 8 kilometers per second. And just to put that in context, that's about 18,000 miles per hour. So that's not something you could easily do with your arm. You couldn't throw a baseball with that speed realistically. Also, this isn't something that would necessarily happen within the atmosphere, right? You couldn't throw a baseball on the surface of the planet and have it orbit the planet because there's air in our atmosphere, right? So drag would act on the ball, would slow it down. If you were throwing something at 18,000 miles per hour, that's actually going to pretty much, the amount of friction that would come from traveling through the air would disintegrate that projectile eventually. It wouldn't be the nuclear explosion that we saw in the Do Now, that was speed of light, but it wouldn't be very good for the projectile. And so you have to get out of the atmosphere. We have to get 150 kilometers up. If you're outside the atmosphere, now there's no air to resist anymore. And so that's where things are usually orbiting. That's why technological satellites and space shuttles and the International Space Station are sent up at least that high, so that they can then achieve this speed of at least 18,000 miles per hour, and they can constantly orbit around the planet. And they usually make corrections to make sure that they're continuing to fall around the planet. Now, again, I know I've thrown a lot at you here with this review, but if you don't take anything else away from this, what I want you to understand is that it's a really common misconception to think that when you're 150 kilometers off the surface of the Earth out in space, that there's less gravity, that there's no gravity. That is not the case, right? High altitudes, objects are not under lower gravity. It's just because they have this really high tangential velocity. They are going sideways, parallel to the Earth, really, really fast, at least 18,000 miles per hour. This is why satellites, they circle the Earth every 90 minutes. They're going really, really fast. And that is what keeps them in orbit. And that's why astronauts experience weightlessness, because they're basically in constant free fall inside of a shuttle or inside the space station. So again, it gets back at that idea of tangential velocity. So I'll show you a short little animation. Should be able to pull this up on Flipgrid. Or sorry, on Edpuzzle. I think I created this through. That I think kind of explains this well. So you can see that the projectile is being launched from multiple different angles, and it hits the ground repeatedly, but then eventually you get that perfect angle, or that, I should say, the amount of speed. It's thrown at just the right amount of horizontal speed that it continually moves around the planet. Just to pause it there at that last point, you can see it traveling all the way around in a full circle. And so that is orbit, right? That would then be considered a satellite. Again, this is assuming that there's no drag. This would have to be outside the atmosphere, which again, on Earth, you have to get about 150 kilometers straight up in order to achieve that. And so this is why when we're trying to send something like a space shuttle into space, they need all that rocketry to first get it that high up, right? 150 kilometers off the ground, but then also to then accelerate whatever the shuttle or the space station or whatever to that 18,000 miles per hour, so that it's continually falling around the planet. Okay, So those are the main things from those 3 sections of chapter 5. You'll be reading those as homework too to try and reinforce that. Any questions on that? Okay. Again, you'll have some homework questions related to that as well. All right, the last thing then that I want to use the remaining class time for, which you can at least get started on, is Rube Goldberg project related. Specifically, all I want you to do right now is work on collecting materials. So the last task on the list, this is number 5 right here, Rube Goldberg work. By the end of the week, I'm hoping that you will have your simple machine made. So this isn't the complicated one. We're going to be working on that till the term ends. But this is just going to be kind of a fun first attempt. I want you to test fire a few things. I've collected a couple of videos. There's about 6 different videos of simple Rube Goldberg machines that have been done by students who had a similar assignment and project to what we're doing, and also some people who just like to work on these things. Some of these are kind of elaborate, not something I would expect you to do, but I think they'll give you some ideas of how you can use materials that might be around your house. The last video is the one, again, that I made that I showed you in our previous lesson before we went on spring long weekend. So your goal is to just try to figure out what you have at home that you can use. So think about, again, hardcover books, if you've got domino sets with your board games and stuff, any athletic equipment like golf balls, lacrosse balls, tennis balls, dog toys, children's toys. If you have like a train set or toy cars, those really work well. And household appliances have some cool features. Like if you have one of those vacuums that has a retractable wire, there's also a little button you can hit it and it sucks the wire back up. That could be something to use as part of a Rube Goldberg machine. A lot of the examples you'll see, they use those multi-plug strips that have this sort of on-off switch. If you can get something to fall on that switch and you have something like a fan plugged in or a light, it can activate those things. So just ideas you can get. So the assignment that I want you to work on is just to watch a few of these videos. You don't have to watch all of them. And then look around your house and try to gather materials you can use to make a simple Rube Goldberg machine. This is just non-permanent, something you could set up on a table or on the floor, run it once, and see if it works. And right now, although all you need to do right now is just take a picture of the material. So you don't have to build a machine. I just want you to figure out what you've got at home that you can use, put it all in a pile, take a picture of it, and then there's an assignment right here, simple Rube Goldberg machine materials. You're just gonna submit that photo. It's just a quick 5-point homework assignment. It's not something you have to put together. I mean, if you want to try to put the machine together and try it, great. But right now, all I'm expecting is materials. So watch some of the videos, look around your house for what you've got materials-wise, and take a picture of the materials and submit that. That's all you need to do. The only other homework is just, as I said, the Hewitt reading. You'll be reading Hewitt chapter 5.9 through 5.11, and I'd like you to answer reading check questions from page 116, same source of questions we've been using for everything so far, questions 21, 23, 24, and 25. Okay, so I won't hold you here. I would like you to work on collecting materials right now. Use the last 5 minutes that we've got to work on that and watch the videos, but otherwise you can submit that as homework. So if you want to leave, you're all set. I'll hang around here to answer questions. But that's it. Thank you very much. Have a good day.
Thank you.
Thank you.